Hi, everybody. Here to talk about the lost art of database design and database design considerations for when you're building applications. Right now, we are in a spot where people think that the databases are just part of the commoditized infrastructure. But unfortunately, that leads us to a lot of problems, and I'm going to talk to you about it. But first, let me introduce myself. I am Matt Yonkovit, head of open source strategy here at Percona, and you can find me on all of the socials everywhere. Follow me on YouTube, LinkedIn, Twitter, anywhere that Percona is. Check out our podcast. Love to hear if we could get some better guests. You're interested in participating. Would love you to like and subscribe to the podcast. You can drop me an email at thehoss@percona.com if you are interested. So, we're talking about database design here. Let's get going. The first thing I want to do is say that a lot of this is going to be captain obvious if you have been in the database space for a long time. That's okay, because there are a lot of people out there who have never heard why they should focus on designing their databases and their database infrastructure a little better. So, multiple people can benefit from this talk. Great. So, let's start with this thought, okay? If you are designing for success, what you decide before you write any code is going to have a huge, if not the biggest, impact on the scalability and stability of your application, right? Of the project that you're working on. So, right now, as you're starting to work and think things through, the decisions you make are going to cascade throughout your application's life cycle. Now, think of it like this, okay? Some failures are easier to fix than others. If a drive fails, you replace the drive. If you need to get a bigger instance because you're hitting CPU limits, you upgrade to the next, instance size. But if you've designed a piece of crap, it's really hard to uncrapify it. Is that a word? I think it should be. So you need to go back and rebuild a lot of what you already did, and it has a massive impact. And a lot of what we do is super connected, okay? There are pieces that are connected throughout our infrastructure. Apps nowadays are no longer a single stack. They are no longer a single component. They're made up of many, a multiverse of different diverse services. And when you start to design, you need to ask yourself and decide on some simple things. One of them is, which stack are you going to be building, right? And that really starts to, what are you building? How is it going to be used? Where are you going to store data? Do you even have choices in many cases, right? So when you start to explore, what you're trying to do, you're going to decide on programming languages. You're going to decide on databases. You're going to decide on, different components, right? If you can. Sometimes if you work at a company, they might be like, you must use Java and you must use Oracle and you must use this, and right? And so they're going to dictate a lot of the choices from the infrastructure standpoint. And you need to understand where your limits are and what you're trying to accomplish before you can make some critical decisions. Now, if you are an old school developer, you probably have seen apps that look something like this, right? You have an app, person connects to a phone, browser, whatever, comes to a web server, hits database, okay? And when you look at deciding on what you're going to build and starting to think through the implications of the different technology, a lot of people look at this and they will make some concrete and generally reasonable assumptions on what this looks like and what sort of components they're going to use. I'm going to use Node.js. I'm going to use MongoDB. I'm going to, use React in the front end. Done. Boom. And that is the extent of what they've thought through. Now, the issue is, realistically, most apps now look something like this. Okay, let's assume this is a phone game or something, mobile game. Okay, so you've got an app that's on the phone. It has its core app web server type activity. It's got a database. But then there's a third-party authentication service. There's a third-party leaderboard, or maybe a separate service that you built for multiple games. There's a chat system for the ecosystem. There's ads that you're displaying. All of these different components actually make up what you're trying to accomplish. And so when you're looking rather myopically at this graph or this architecture, it seems fairly straightforward and you can make some decisions. But if you actually look at the holistic view, you might start to figure out that, maybe there are some better choices for me to make, because, this might be something that your authentication is built on, technology that's, supported in one environment and not another. Or it might be that your libraries of choice might not have the hook-ins to, certain, systems here. So understanding that, like, this is a bigger, broader picture and there are multiple components to consider is a critical, first step. And a lot of times what decisions are made in these subcomponents and the overall architecture, it's not up to you. And this gets into what I call stack politics. Oftentimes you don't get a choice, right? Oftentimes you will be dictated certain changes and you will have to live with them. So understanding as you start to build and design out what your infrastructure and your application is going to do, especially on the database side, and what you can and cannot do, what the limitations are incredibly important. Now, keep in mind that as you do that, you have to also understand that the small things matter greatly. So it might seem insignificant to make certain decisions, but those certain decisions can have massive cascading impacts. A good example of this is I did some testing and I was testing different Python drivers and different MySQL drivers for Python. You can see that there's actually a pretty significant performance difference between certain Python drivers and certain versions of Python. So the combination of different components can often have a pretty significant impact on the performance and the scalability of your systems. So when we go back to the big graph of this, you have to understand that each one of these connected lines, right, and each box that we see will have another set of boxes underneath it, and each one of those has to be verified and vetted that they actually work well together and that they're designed in a way that you're taking advantage of each of those systems appropriately. Because if one of those boxes tends to use Python 3.10 in the MySQL connector, where another one uses MySQL 3.10 with the MySQL client, a performance difference of almost 70% difference could create some artificial bottlenecks. So understanding those components, how they all work together, is incredibly important. Now, we're going to talk about the actual physical database design in a second, but I wanted to point out how incredibly important the entire ecosystem is in understanding the infrastructure and how the components play together. But I also want to point out that, especially with this particular slide, that sometimes just assuming things work right doesn't necessarily mean they will. And this is a philosophy that you'll often see when you're building out your schemas, you're building out your applications, you're building out your code, that people will assume just because something works means that it works well enough and it won't break or it isn't problematic. I recently had a problem with some plumbing, and the plumbing was working fine for 2 years, but underneath the floorboards it was leaking water, and it wasn't until 2 years that enough had leaked to cause a problem. Doesn't mean that my plumbing was set up correctly. It just means that it worked for 2 years without manifesting the real problem that it had. And that often happens in the application design space right now. And so understanding all the different components and getting a clear picture is fundamental to understanding how you should build the data infrastructure as well. Now, you don't want to just put blind trust in technology. Okay, you just can't assume that everything is going to work out of the box. But I do want to say most of the success and failure of projects and of applications is not due to the technology choices. It sometimes is, but it's very rare because, when you choose a database or a cloud provider or a JavaScript library, okay, all of these components within the stack, they can be made to work in a variety of conditions, right? It really is not about whether they can do the work in many cases. It's about how you've designed and implemented it. Because an application or, a game or whatever, its success is tied to the end user experience, not necessarily what libraries you picked. And part of the job as architects, as designers, as infrastructure folks is to make sure that we have set up the systems and designed the systems that lead to the greatest path to, customer happiness, delight, whatever you want to call it. And that means that we're looking at things like availability, security, performance, right? These are the things that are going to impact the end user experience, and that's what matters more than anything else. And, looking specifically at the database, there is a database out there for all kinds of different workloads, okay? I'm not going to get into which database is best for which workloads. That's beyond the scope of this. But I do want to point out that you can make any database work for almost any workload. Doesn't mean you should, because, it's like, putting a tiny engine in a sports car, right? Yeah, it can go down the street. It can go 50 miles an hour, but the car was supposed to go 300 miles an hour. You're not going to meet the expectations. And so when it comes to, choosing a database or a cloud provider, you have to understand that the choice of one over the other isn't going to dictate your success. It doesn't matter how awesome they say that they are performant and scalable and have all of this other stuff. That's wonderful. That's great. But if you design it poorly, you're not going to be able to achieve the level of success that they are telling you you can. And that's critical. So it's really about trusting but verifying. So when someone says that the scalability of my database is 1,000 times greater than any other database on the planet, you can trust them on that, but you need to verify it, especially that it does in your environment. Same thing with cloud providers, same thing with SaaS providers. Anybody who's in that architecture design components that we had out there, any component there, trust but verify that you're getting what you expect out of them. Because oftentimes you might not be. And, when we have these technologies that we're implementing and adding into our ecosystem and our infrastructure, you have to understand that even though many may claim to be fully managed or self-managed or zero management, you still have to have someone who is responsible for it, especially in the database space, okay, but in other spaces as well. So who manages it and understanding who is ultimately responsible for those activities when it comes to, ensuring and trusting but verifying you're getting the results and the things that you want. Who is it? And what about the cloud? Well, we'll get to that in a second, but, you still need these functions in the cloud. It just changes maybe what some of their day-to-day responsibilities are. So as we start to think about who's managing, your databases, who's managing the technology, we should probably start to think about like what sort of database we want to choose or use for this particular application. And those are going to come down to specific questions, right? You're going to start looking at what components you need to rely, that are going to connect to the database. How are they going to use it? What sort of, skills do you have in-house? What happens if the database goes down? What happens if you lose a few seconds worth of data, right? So all of these questions are things that you need to think about before you choose the database technology that's part of your stack. And that's going to drive each one of those components. It might be multiple databases. Each one of those components I showed you might get their own database, might be a different technology. You should ask these questions for all of them. But not only do you want to understand the database, side of things from how is it going to be used, but you also have to understand the capacity planning side of this. Okay? How much data will you store? What will it look like in 1 to 2 years? Is data transient? Is it going to come and go? Do you need streaming? Like, thinking about that architecture picture that I showed you, right? How data is flowing through them and how the data is stored in each one of them, that's going to help you design a better application. It's going to help you pick the right database. It's going to help you design a better database structure for your data. All critically important. All critically important. You also need to think about that ecosystem again, right? So we go back to that picture of, all of the different applications, right? So we go back to this guy right here. You look at this. How are third parties going to access your data, right? How are third parties going to, pull data out, use it, retrieve it, do whatever? One too far. So third-party plugin software, how you need to integrate. Think about it, plan for it, understand that that's critical. Now, when we talk about databases in the clouds, you have to follow that same trust but verify, and you have to understand you still need to manage. Because if you aren't managing, then you are potentially scaling your system by your credit card, right? Because there is a shared responsibility model. So again, trust but verify. So just because you've chosen a cloud provider to manage your databases does not mean that you are free from designing, architecting, or ensuring that it is working properly. Okay? All critically important things for you as you design something. Daniel Nichters gave a presentation and has a book out on efficient MySQL performance where he published this graph. I grabbed it from his presentation. Excellent kind of visual just to kind of outline what sort of things you're responsible for versus the cloud. And so that's something that all people who are building a new app should consider. Now, you might also be considering whether you want to run your cloud or your database infrastructure on, Kubernetes or in a cloud native type way, right? And so you can, and a lot of people are starting to be very successful at doing this. But you need to consider, a couple things, right? So each of the databases will have different levels of support for Kubernetes and will operate slightly differently. And the scalability will also be very dependent on the technology, right? So how you're looking to grow the application. And remember, I got to some of those questions about, hey, we're designing, the system. What does this look like in 2 years? If you are looking for sharding and scaling features, maybe MySQL and Postgres out of the box don't have that. Maybe you need to add extensions. Maybe you need to look at, some alternatives. So the workload patterns and what they'll look like in a couple of years will help you choose the right technology. Now, when we talk about clustering, sharding, there's this concept of NewSQL. And so I wanted to provide a word or two for those who might not be aware of what it is. But it's something that is important. So first on this is to understand kind of the concept between sharding and clustering. Okay. And so a key concept when we're talking about databases and data growth is the more data you store and use, the slower your database generally gets. I'm just going to throw that out there because databases are heavily dependent on what can be stored in memory, and the more data that's in memory, the faster it is to access. There's definitely, memory faster than disk. It's a universal constant that's been around forever. So you want more stuff to fit in memory, and the larger your data set, the less can fit into memory. But also, the more data you have on disk, the more your backups take, the longer it takes to do operations, the more costly it is. So there's all kinds of implications. So basically, the more data you store, the slower the database becomes. Most databases all do this. Now, there is this concept that's called sharding. And what sharding does is it takes your data and it breaks it up into smaller data and spreads it across multiple machines. Okay? Mongo, for instance, has built-in sharding into its database. Postgres and MySQL do not. However, there are new databases or new technologies that bring sharding or clustering like solutions. Now, the difference between clustering and sharding is clustering is taking servers and combining them to all appear as one, so you have multiple servers that all appear as one, whereas sharding is splitting your data amongst multiple nodes. Now, when we talk about some of the new school databases that are out there are new databases that are coming along that are implementing a sharding plus clustering type setup. So TiDB, Cockroach, Yugabyte, great promise, excellent performance on some workloads, but sharding requires your application to be written and designed a certain way to take advantage of it fully. And it assumes that certain functions or features or things aren't necessarily done within that particular database, right? So when you think about sharding, let me go back to my sharding slide really quick here. If you're going to select an aggregate across multiple shards, and let's say you have 10 shards, you will have to go down to each server, pull individual pieces of data, then aggregate them back up, and then continue to munge them up until you get the final result. That's not necessarily great for sub-second transactional processing. It could be fine to incur that impact for reporting or analytics workloads where it doesn't matter as much. But there are some fundamental things that you just need to be made aware of. Certain things aren't going to work right, especially if you're not selecting off of the shard key. That's probably a better example here. If shard key, for instance, is last name, and this is how your sharded system or one of the new SQLs set up is to use that last name or whatever, and you select first name, then you're going to have to hit all the shards and then aggregate that data back. So this is just a small example. Not all of them have the same limitations, but that type of thing. Now, sharding, there are systems like VTES, which is an extension for Postgres, VTES, which is MySQL framework, and then Citus, which is a Postgres plugin. Sorry, reverse those, where data is split amongst the nodes, and it requires more structure around the database. It's not a database in and of itself. Now, TiDB, Cockroach, and Yugabyte are compatible with open source technology. So TiDB, MySQL compatible, Cockroach and Yugabyte Postgres compatible. So they have compatibility, but they are not 100% MySQL Postgres, whereas VTES and Citus are Postgres and MySQL, just with additional technology around it. And then I mentioned there's also other technologies like Mongo, which has its own built-in sharding as well. So mileage will differ on these, but these require you to also think schema structures, workload, data access. All of those things are universal, whether you are using one of these technologies or not. And that's where it really comes down to that design of the systems, and the database matters. Okay. I asked our engineers, our support engineers, our managed service engineers, what's the number one issue that they see over and over again? And you know what? Their number one issue is always poor database design. Okay. That's the most common issue that causes the most problems amongst the largest subset of users. And that has a variety of, causes, right? Bad data type selection, poor schema design, over-reliance on ORM frameworks, under or oversized hardware, storing more data than is needed. I've also heard that the Rube Goldberg, infrastructure design also comes into play. That being something overly complex, you should never use it. And that gets back to a lot of what we were talking about, those understanding the different components and how they interact with one another to choose the appropriate database. So why do data types matter? You might hear this harped on quite a bit. A lot of people might be like, I'm so sick of data types. Just shut up about data types. I'm just going to use whatever. But remember, I said earlier, memory is faster than solid state disk, which is faster than rotational storage. All databases are memory hungry, okay? Because the performance is when your data is in memory. That's where you're going to get your greatest performance. So the more data that you are storing on disk, the less can fit into memory. And the wider or the fatter the rows are, the less rows you can store into memory. Okay? And this comes at a time when we're not only talking about data types, but we're also seeing an explosion in the amount of data that people are just physically trying to keep around. We're data hoarders. We are keeping data forever. And we never want to clean it up. And so we've got more data, and we know that we need to store things into memory. So when we talk data types, it matters quite a bit. So a good example of this, using MySQL. If you're storing 1, 2, 3, 4, 5, 6, you could store that as a varchar, or you could store that as an int or a big int. Obviously, you would say, well, why wouldn't you store it as a big int? You'd be surprised. It happens. But in this case, you're talking about the difference between 4 bytes and 21 bytes. Well, you might be like, that's not that many. But over 100 million or a trillion data points, that adds up to a significant amount of overhead. Now, thankfully, the databases themselves have several different types of specialized data types for all kinds of different things. Like there's a data type for storing IP addresses. There's a data type for storing, common sets of data. Each of the data types are designed to improve the footprint or decrease the footprint of the data that they're storing and make it more efficient to process and handle that data. So make sure that no matter what database you're using, you're thinking about that. But let me give you an example of why this really, really matters. Okay. We worked with a social media company, really big social media company, still around. You probably use them every day. Won't say who they are. But they were storing everything that they had in as your email address. So everything was primary keyed or keyed off of your email address. When you sign up with your email address. It takes that email address. It creates your user based on the email address is the primary key. It creates other information using all of the linkage with the primary key. Now in MySQL, which this happened to be, MySQL is even a little more conscious of using the right data types, especially for primary keys, because the primary key is stored as a pointer back in every subsequent index you create. So imagine you have this 100-byte, field that is your primary key, and then every subsequent index, even if that index is what is your age, you're just doing I want to get everybody who's under 18. It will also then store everyone's email address. So you can see how that blows up. Now, for that particular company, they were experiencing some significant problems with not only performance, but also runaway storage costs because of this. And so in the end, what we ended up doing was using the primary key as a unique key, that taking the email address, making it a unique key, and then using a CRC32 hash, so that becomes an integer, as well as an auto increment ID as the primary key, which reduced their space. I think it was like 3 or 4 times what they had. So it was a 3-4x reduction in the space alone, and also a 2-3x improvement in all of their query performance. And this gets back to, and we've written about this quite a bit. I would encourage you to go check out our blog for using UUIDs as primary keys, why it's bad. But a lot of applications, especially ORMs, might use a UUID as the primary key for tables. And in the case of MySQL, that is a really inefficient use. It also has a cost in Postgres as well. It's not as significant as MySQL, but it is substantial. So I would encourage you to watch out for using the appropriate data type and making sure that you're using that. But half of you out there, or maybe a quarter of you, are saying, I don't care about schemas because I'm schemaless. And here I'm going to tell you that is marketing material. It is fluff. I don't believe it. You should not believe it either, even if you are using MongoDB. It is not schemaless. That's a quote. You can quote me on it. When we talk about schemaless, we're talking about unstructured data. We're talking about that flexible design. And the issue here is you are trading your flexibility for performance and scalability. And as your data volume increases, these quote unquote flexible systems really, really, really slow down and often will get to the point of being non-functional. Because you are still having to validate that the data is in some sort of structure at some point or another. And so if you are not enforcing the validation, the databases themselves have some logic behind the scenes, the schemaless databases, to try and do some minimal validation. And so the more crazy the structures get, the more work it has to do, which slows things down. But also, a lot of times, even beyond just that happening, you have to push the logic to do the validation up to the application. And so you might be doing double validation in some cases. And that's why most vendors who have a quote-unquote flexible schema or schemaless type of implementation recommend some sort of schema validation and, say that that is absolutely a best practice. So keep that in mind, that even if you are saying, oh, I'm schemaless and flexible, you're just forcing something else to do that, that validation, and you lose a lot of control over your structures, and you're going to have to write code to potentially fix some weirdness. So there is that. Now, as your schema and query design goes, you will start to grow, and you'll eventually outgrow a single server. So how are you going to scale? And understanding that is very important when you're designing your application early, because you can start to think about, like, can I do read-write splitting? Can I take and move data to shards if I want to go sharded later on? Okay. If as I grow, maybe how I'm selecting the data out of my system needs to be changed. I say avoid select stars. I've been at companies where they select everything and then throw away everything but one column, and they oversaturate their network pipeline. Well, as data grows, especially in the quote-unquote schemaless side, where your schema might start very narrow and selecting all the data might be okay, as you get bigger or as you add columns even to a relational table, a select star might become unruly, right? Because let's say right now you just have first name, last name, email address, but then all of a sudden you add a binary column to store someone's picture, and you're using select star. All that binary column is going to get selected and brought to the application, even though the application might not ever use it or need it. And so that could be a significant overhead. Now, of course, we want to talk about indexing, because we can't not talk about indexing, because indexing is probably going to be the number one thing that everyone looks to when they're looking at query performance problems. Assuming that you've chosen the right data setup, you've chosen the right databases, you've set up the workload, you've analyzed the different components, you know how they work together, you're probably at the point now where you've got some queries that are a little slow. So indexes are good. Too many indexes are not good. Okay. There is an overhead to adding indexes. It's really on the insert, update, delete side that you're going to see that overhead really start to creep up if you have too many indexes or have over-indexed. But you don't need an index in every column. You should be looking at what is being selected on most frequently and how it's being used. And that's what you should be looking to index. And you should check, the statistics, whether you're in Postgres or other databases. They all have slightly different ways to do this. Which ones are being used, which ones aren't? If they're not being used, why are they out there, right? You can drop those. And know that each database has their own index types, and there could be indexes specifically for workloads. So Postgres has several that are really interesting for different types of workload. And so understanding how your data is going to be accessed again and how it's going to be used across the whole application, you can choose better indexes for that. Now, let me finalize or wrap up with this, okay? Recapping, if you have the right design, that means that, which database is going to be appropriate for what you're trying to do. You're going to understand the pros and cons of the environment. You're going to understand the workload, the growth, the access patterns, right? You're going to understand how data is being accessed through the system and where it's going to go. And then if you have that, then you can start to think about the data types and the schema itself, and understand that space matters. That's going to have a direct correlation with performance, and you're not going to overthink your structures. And eventually, you're going to then add the right indexes. And so if you're following that process, you're going to have a structure that is not only going to work for you, but it's going to be very scalable and efficient going forward. Thank you for hanging out with me today. Hopefully that was interesting for you all. And don't forget to like and subscribe here at Percona's channel. And check out our podcast. I'd love to hear your feedback. Thanks a bunch.